Welcome to Experiment 2, Thin Layer Chromatography, also known as TLC. In this particular lab, you're going to be working with the difference in attraction between two compounds that you have in, let's say, a mixed sample, and trying to separate them using their polarity differences based on any number of these solvents that you would use for a mobile phase. The mobile phase is going to basically contain two compounds or more. Oftentimes you have a mixture of, let's say, ethyl acetate and hexane in different proportions that are going to have different levels of solubility with the compounds that you're interested in separating. In order to separate those compounds, you have to create essentially a racetrack for them to travel across and to separate from each other in speed, and that is what we have a TLC plate for. So a TLC plate is going to sit in a pool of solvent. This solvent is going to be this mixture of, let's say, ethyl acetate and hexane, but it could be any of these other solvents depending on how polar your compounds are. And when you think about the way that those solvents are interacting with your compound, the more polar your compound is, the more likely it's going to be less attracted to a nonpolar solvent. And conversely, more attracted to the alumina base, or in this case, we're using silica. So that's going to be considered the stationary phase. The stationary phase is essentially the very polar base that your compounds are sitting on and are attracted to, preventing them from moving further along this racetrack to the terminal point where the race will essentially end. The difference in speed that they move is going to give you a difference in polarity that you're going to observe by the different retention factors, or essentially the distance traveled of the sample versus the total distance over the period of time that you're running the samples. So if you have a variety of samples, you can basically see one by one how they fared in the race. If you have a race that ends too early, let's say if you stop the eluent too far before you start, you don't have a good idea of the true difference in polarity that these compounds have. You want them to run a nice far distance in order to actually observe their differences in polarity and their relationship with the eluent, which is dissolving them and moving them up the racetrack, versus the stationary phase, which is actually holding them fast and preventing them from moving quickly. So using these to separate compounds, like I said, is a very classic technique because you can actually dissolve those compounds later on in a similar mixture, like let's say of ethyl acetate and hexane again, and move them through what we call a column, or basically a silica column chromatography experiment, where you can essentially use the information you got about how strongly these are, let's say, adhering to the surface versus moving quickly, to figure out which compounds are going to come out first in fractions that you'll collect out of the other side of a stationary phase or a column. You're going to see the eluent pull out those first compounds that are going to be most soluble in that eluent and least interacting with that silica. The compounds that are going to hold fast are going to instead be the more polar compounds that have a closer and stronger polar interaction with the silica in this case. So if you have, let's say, a variety of different compounds, they might have to go through different stages and phases of this column chromatography, because some of them may be way more polar and some of them may be way less polar. As long as you use a nonpolar eluent or mobile phase, it's going to move quickly, and all of those samples that are more nonpolar are going to move with it and come out first, leaving the polar compounds coming out last, allowing you to create nice pure samples that you can use for whatever else you're going to use them for, depending on what kind of chemical you're talking about. So today we're going to actually work with some thin layer chromatography. I'm going to show you how to spot them, how to run them in a TLC chamber, as well as look at their final retention factor, which you'll calculate in order to identify two compounds that are mixed together from 4 known samples that we will compare them to. We're working with 1 to 3 hexane ethyl acetate because the compounds we're working with today are pretty nonpolar. And the important thing when you're choosing any kind of eluent, remember is just how it works on the plate. You just want to get good separation of your compounds. It doesn't necessarily mean that you have polar or non-polar compounds, although if they don't actually dissolve in this, you're going to have a big problem on your hands. So here's the TLC plate itself. So if you have a TLC plate, it's important when you're working with it that you also are careful not to do any kind of, let's say, touching with bare hands or contamination in any way, because that can severely impact the quality of your final product and your results. You also want to try to pick a TLC plate. This one has some of the silica chipped off the corner, that has as even a coating of silica as possible, at least on one side, so that the eluent will flow evenly and will diffuse straight up instead of diagonally. If it flows diagonally, you could have, let's say if you spot here, your sample being pushed across the plate into the line of the other sample. So you take a ruler and you mark the starting point for all of your samples that you'll be using. Today, we're going to be using aspirin, ibuprofen, acetaminophen, and caffeine in order to sort of compare their final resting points on the TLC plate. You want to make sure that you use a pencil for this marking of the starting point. You want to be clear and consistent across the entire plate, so we'll try to get it lined up as parallel as possible, or perpendicular to the sides of the TLC plate. And you want to give yourself about 1 centimeter in order to have a very even starting point. Try to avoid chipping off any of the silica if you can. Sometimes it's tough. This is not perfectly straight, but it's pretty good. And that's all that matters. You'll try to make sure that you line up and correct that where you place your sample, because that's actually what matters. So here's a question. Why do you think that you use pencil instead of pen for this? The important thing for using any kind of TLC plate is that anything that's soluble in an organic compound is going to move up the plate. The graphite inside of this pencil is non-polar, but it's not going to move from its original point. So that's why you always want to use this, let's say, any kind of graphite-based pencil, because it's going to be good for making marks without any expecting or worrying that they're going to move. Inks are definitely going to be dissolved, and so you don't want to ever use a pen for this. One reason that I actually worked with this ruler to sort of plan about, let's say, 1.5 centimeters to start is because you don't want any of the solution that we're going to use in our TLC chamber to ever overlap over the sides or splash up onto the TLC plate. That could prematurely start the actual process of the TLC and negatively affect our results, creating less separation, or if you actually allow the eluent to lap over the starting point, it's going to wash all of the starting products back to the eluent pool, which is not what you want. You're just going to have a mix of all of the different compounds you had on the starting lines already mixed together and moving up and down the plate, and it's going to just cause a lot of other problems. So you have these fresh capillary tubes, and they're ready to go. And now we're going to look at our samples. So ideally, you would pour a smaller sample out of these and put it into a container for yourself and label it. But today I'm going to use an individual capillary tube for each of the samples, so we don't have to worry about that. You want to be very careful to never contaminate any kind of pure samples. If you're moving from, let's say, the aspirin to the ibuprofen, you don't want either of those to mix, right? So we're going to start by blotting the aspirin. And in general, if you have time beforehand, you always want to work with an extremely dilute sample when you're doing any kind of TLC. You don't want a gigantic spot on your plate. You want a nice, small little place where your sample is moving from. You want a nice, small spot where that sample ends up in the final product. So with a solution as dilute as possible, you blot in one spot and only one spot on your TLC plate. We're going to consider aspirin to be number 1 on this first plate. You can also label it at the top if you want. Try to make sure that you keep that spot in as small a point as possible because you don't want it to spread itself out during the run. Next, we're going to do ibuprofen. So I'm going to label the first part 1, and hopefully I don't confuse that with an I for ibuprofen. I'll just make it into an A. That's fine for aspirin. And then I'm going to take another capillary tube and go over to the ibuprofen. So if you remember what I said about correcting your samples, just try to make sure that you put them at the same even level on the plate where they finally end up getting spotted. It's good to keep a good amount of distance between them two because any overlap will be a serious problem. Don't allow the spot that the material is moving out to become too big. You want it to be a nice little spot at the starting line. So now that you have your TLC plate prepared and labeled, we're going to put a little eye there. We're going to take our TLC chamber and sort of take a look at how it's designed. So it's usually good to have a TLC chamber that can be closed. This allows vapor pressure to build up and kind of pushes the eluent along evenly as it goes up the plate. You also want a chamber that's going to be easy to get into if you need to. You don't want to allow your sample or your TLC plate to run too long. And if you let it, let's say, run too long, as I mentioned before, you'll have the samples run past the point where they would have been expected to stop based on the consistent results you were hoping for. So if you take your TLC plate and place it in ahead of time and pour in solution, that's going to be less than ideal. And here's why. You want to essentially consider the point that you put that TLC plate into the chamber to be the very starting point. So you want to make sure that you add enough of the eluent first in order for everything to be ready to go. And once you put that TLC plate in, it's go time. I'm actually going to put it in for a second only because I want to see how high I should make that eluent. I don't want the eluent to be any higher in the jar than below where the samples begin because it'll prevent any kind of washing over the samples and cross-contamination. So it's going to be pretty shallow. You don't need much. You really just need enough of the solution to coat the plate, and that is it. You want to avoid too much extra solution if you can. It doesn't help at all. Also be careful to maybe work in a hood if you can. Some of these solvents are a little noxious and toxic. Hexanes are not exactly good for you. Ethyl acetate's not so bad. It's in wine and grapes, but not too much. So here we go. We're going to take our sample and place it in the TLC chamber. And you're going to let it sit down slowly. And once it is going, you are ready to start. Already you can kind of get closer here and see that it's sort of moving unevenly. Hopefully that won't cause any problems. Ideally, it would move in a perfectly even flat line. But even that small defect in the corner It's causing some uneven diffusion. So hopefully it's not too bad. You're going to put the lid on the jar, but make sure you don't make it too tight. You want to be able to get in there as soon as possible once you decide that the run is over. Don't allow your TLC plate to run too long by walking away or doing something else. You want to keep an eye on it the entire time that you're working with the plate. Otherwise, you might have to start all over again, and that's no good. All right, so it looks like we have this done. It just needs to come out. Okay, hopefully we'll get some good results. And here we just let it sit and dry. While it's sitting and drying, you can get started on the second TLC plate, which I will do. For now, we're just gonna get going with the next plate. Try to pick one out that has a more even coat on the bottom. I'm gonna be very gentle and not break any of the silica. And gonna draw those lines again. So you want to move about, let's say, 1.5 centimeters, similar starting point. And you will draw your line right here. Doesn't need to be too thick, just needs to be able to be seen so you can do consistent work. Next, we're going to go to our next samples. So we have acetaminophen. In fact, in order to avoid confusing any of these samples, I'm just going to label this 1 for our first trial. So for our second trial, I'll put a 2 once it's out ready to dry. But acetaminophen is going to have an A, so we'll put that at the top of the sample in the silica. And we will take the lid off and get ourselves a little drink here. Stuff can be such a headache sometimes. The acetaminophen joke. Anyways, so you have a small spot for your acetaminophen. Remember to keep it nice and tight here. You don't want it to be wide. You want it to be in just one little spot. We'll make sure we drain all of our sample. The capillary tube will actually pull quite a bit in, so you will have plenty to work with. Don't just jab your sample, otherwise it's going to leak over all over your plate. Close up that caffeine, and we'll get the TLC plate ready to go for the next trial. Now there's plenty of solvent still in there. I'm gonna add a tiny bit more just to make up for whatever we lost through either evaporation or from soaking into the plate and coming out with it. Just a little bit. You don't need much in there at all. Big mistake I usually see people just getting used to this stuff doing. Close up these plates too to keep them clean. And we will begin. Looks like we're traveling up the side evenly there, which is ideal. It's good to sometimes plot closer to the center of the plate, just because the edges can pick up the solvent a little bit faster sometimes, if you can see that. And just gonna loosely put on the lid and try not to bump it over. If you bump it, and by over, it is over. So now, you might not always remember where the solvent front ended on your plates. I remember that it ended just right before the A and the I, but in general, you should always try to label it as soon as the plate comes out of the TLC chamber. That's where the solvent ended. This will help us calculate the RF, or retention factor, later on. And now, we wait. All right, so we've been waiting about 5-10 minutes, and the TLC plate has gone all the way up to close to the A and the C. a little bit short of them, but that's fine. It's more of a proportion than it is an actual distance. So we'll open up this TLC chamber very carefully so as not to disturb the eluent, and we will reach in and grab that plate. So since it's different than the last plate, I'm going to take this ruler or just a pencil and make a line where the solvent line ended. It's important to make sure that you do that while you remember, especially while you're still learning, because you can't expect the endpoint to basically move from where it was supposed to be between these two much compared to the proportion of distance that those individual compounds are traveling. To make that a little bit more clear, the actual RF or retention factor is just going to be the fraction of the distance that those individual compounds moved relative to their starting point. And so if you start a little bit higher, you're going to have a slightly later point. If you start a little bit lower, you're going to have a slightly earlier point. In this case, it also is just a fraction of how far they move relative to the starting point and the total distance traveled. Back. And we're going to start the unknown sample for this TLC experiment. What we're going to use today is one of these 4 unknowns. Some of them are containing pure compounds, and some of them are not pure. Some of them have more than one of these compounds, for example, versus just one single compound as you might find in others. So the anderson is the one that I think will be the best choice today. And the way that I would figure out the compounds inside of anderson is I would actually take a blot of this, which is dissolved in methanol and was prepared according to these other pure samples. That can cause some minor effects if concentration is vastly different. And I'm going to sample this anderson and plot it onto a TLC plate, just like I had prepared these other 2. All right, so we have the starting point. We're going to label this with a U and get it started in the TLC chamber. Once you get going and have everything set up here, it's actually a pretty quick process. It'll also make it a lot easier for us because you have only one sample going up only one plate. That's pretty useful if we're just using RF factor to identify our compounds. So next thing is next. We'll take our unknown and put it into our chamber. Always set it as gently as possible. Always set it as gently as possible in order to prevent any kind of splashing. I did my best here. We got a little bit of diffusion on the sides happening faster, but since there's only one sample, we're not as worried about it getting scattered across the lateral part of this stationary thing. Perfect. Perfect. Okay. All right. So we've been having this individual. So we've been letting this TLC plate run for about 5 minutes now, and our unknown is ready to be unveiled. Let us take a look. I will grab our UV lamp. The important thing about UV lamps is really easy to forget and leave them on. So we'll make sure that when you're working with any kind of UV lamp, you're careful not to leave it on for too long, but you operate on pretty decently high voltage because it takes a lot of energy to make UV light. And you want to try and turn it off whenever you can because it will just heat up and cause all kinds of problems. So here's where the UV comes from before we turn it on. And you can actually see the UV on the surface of a countertop if you turn it on as it reflects back. But you should also not look directly at the light because it's not good for you. All right. So here we are with our original mixtures of the products or samples. And the first plate, as you can see, had some issues. Plate number 2 came out a lot better. We had the original spotted lines, and there might have been some impurity that showed up a little bit later on the second plate right here. And then this third plate had a mixture of 2 compounds, which we're going to identify. If you look across this set of different choices, there are a couple different compounds that sort of seem to be in a similar spot. I'll give you a second to take a guess on that. So let's take a look at these 3 and try to compare them just by looks. If you take a look at these right next to each other, you can kind of get an idea of what might be the actual identity of the unknown. The caffeine appears to show up really close to the starting line in both the pure sample and the unknown. So that's a good possibility. We'll use the RF to help calculate and justify that idea. The other sample, so in this case acetaminophen, is a little bit further than the caffeine and has a darker appearance because it's absorbing more of the UV light. So since it's a little bit closer and a little bit further from the terminal point, you're gonna probably not assume that this other sample in the unknown comes from that acetaminophen. Probably instead, this might be, what do you think? Between the ibuprofen and the aspirin, looks a lot more close to the aspirin. Again, we'll use, even though this is not a perfect plate, it'll have to do for now, this sample to justify that based on the RF value. So between all of these different compounds, another thing worth noting is the polarity. You can see that some of these compounds are a little bit more polar than the other ones, and they stayed either closer or further from the end. What do you think? So if you guessed that they were actually more polar and staying closer to the starting line, you were correct. The eluent swept away the more nonpolar compounds and took them to the end of the TLC plate. All right, let's get to calculating some RF values. So looking at our TLC plates, you can see that I've taken a pencil and I've marked all of the centers of these spots that were on the plates with the UV light. It's much harder to actually measure those spots if you're working with the UV lamp at the same time, and so I highly recommend doing that instead of trying to work with both a ruler and a UV lamp. You're probably just going to get bad measurements. So we're going to work in terms of centimeters because we work with a metric system in this house. And we will look at these distances based on the original spot point, which can be easy to find if you just look in the silica for where you maybe have touched it or dug in with your capillary tube. And we're going to take our spots and measure them out. So for our unknown, spot 1 will be the lower spot. And we will take the measurement of, let's say, we'll start at the bottom of the ruler to make this easy. So we have about 1 centimeter. It's less than 1 centimeter, so it's about maybe about 6.8 millimeters. millimeters over the total distance, which is close to about 42.5 millimeters. Or if you want to convert that to centimeters, millimeters just happen to work better in this case for these plates. So if you have spot 2, which you do, you calculate that in a similar manner. So we look around and we have our first unknown spot, and we look at these 4 values of the knowns. You have 0.650, 0.841, 0.332, and 0.193. So this one is drastically closer to one in particular, and that one is going to be the caffeine. Caffeine is 0.193, this is 0.160, so it's only a difference of 0.033, right? So that's pretty close, and definitely going to be the best candidate for what possible compound is in that unknown. So that's going to be one of our unknowns. And the other unknown is 0.631. Of these 4, which is the closest to that retention factor? If you guessed the aspirin, then you are correct. So aspirin appears to be the other compound in that mixture. One thing that's worth remembering is that the further the distance you get in any of these different kinds of trials and different kinds of TLC methods, is you want to get maximum separation between the samples. Another big important thing, as you noticed when we actually looked at the TLC plates themselves, is there were some pretty big blobs that were still sitting in that TLC plate when we looked at it. And the smaller those individual blobs are, the easier it will be to actually calculate what the RF is. You're gonna have to decide, are you gonna measure from the bottom, are you gonna measure from the top, are you gonna measure from the middle of that spot? The smaller the spot, the closer those individual 3 possible points are gonna be the same. And when they're the same, it's gonna be really easy to sort of have consistent results if you're using exactly the same mixture of solvents. As soon as you change the blend here though, from 1 to 3 hexane ethyl acetate to say 1 to 6 or 1 to 18, depending on what runs the best for the sample, you're gonna get different results. That could enhance a result. You could get actually better separation with the different blend, or you could get worse separation. Maybe you won't actually have the solvent front even move any of the compounds at all. If it doesn't move the compounds, it's probably a good sign that your solvent isn't polar enough. And if it's not polar enough, then you're gonna just have to increase the polarity so that it can move relative to the silica base that you're having having those samples move across up the TLC plate. Well, other than that, you're all set. Have a great, great day. Okay. You already have it going?
Yeah.
Okay. Excellent. I'll just put that in the outtakes.
Yeah.